Good afternoon, boys and girls. It is a Saturday, the 24th of October, and I welcome you to another lesson on Technical Sciences, grade 12. Today, we are concluding the topic on light. Remember, this is a topic from paper 2 of your examination. And really, it's one of the topics where you can really do well because it is quite theoretical and at the same time, it is quite practical. So for today, my dear learners, it is a question and answer session. In this session, my dear learners, we are purely going to look at questions, and most of the questions that I have for you are from previous examination papers. And the idea behind this is really to help you see how we ask you the questions, to help you to analyze the question, and to help you and guide you into how you need to present your answer such that you get full marks, and also to give you an idea of where the answer actually lies based on the question. So it is really a session where we analyze, we think critically about what we are being asked, we think about what the examination guideline tells us, and we check how we need to present an answer so that we are able to get full marks. Now, I need to say more to say that in this topic, you need to be able to define quite a number of terms. And the terms are very important. The terms are very important. And for you to know the terms, you need to have your examination guidelines at all material times when you are studying. This is because the examination guidelines are going to guide you in terms of what you need to know and how the definitions are going to be marked. Remember, we mark the definitions that you get from the examination guidelines. And that is purely for the purpose of marking. And we are also sure that the definitions are full. And hence, we do not recommend for you to use definitions in the textbook. And I am not saying that definitions in the textbooks are not correct. All I'm simply saying is it is safer to use those that are in the examination guidelines because you are definitely sure that if you have used that one, then you will get all the marks. So please be aware of that. Now, for today, like I said, it's a question and answer session, and I really want us to look at the questions, analyze them, and answer them, and see how marks are allocated for a given type of question. And I want us to also fine-tune our answers to give more detail in how we explain things. Furthermore, in this topic, we are required to draw because you can be asked to draw a diagram that would reflect, that would show reflection, refraction, dispersion, transmission of light through a convex lens, transmission of light through a concave lens. So all of that, my dear learners, are the drawings that we need to be able to draw. And we must then be detailed in how we draw and know exactly what is marked in those particular drawings. when you are actually tracking the path of a light ray. Now, that is in a nutshell the summary of what I wanted to tell you in terms of what you should expect for this lesson today. And I want us to then look at the structure of the lesson for today. So, another quick review to check what is required of us in terms of light as per the examination guidelines. And my dear learners, really dealing with this section is a form of good revision on everything that we have learned. It is because when we go through this, we are able to remind ourselves of everything that we need to know, and we try and remember that off from our head. Then in the features of the topic, we will be learning light, and we will be doing that through questions on light. So with the questions that we are going to deal with, we are going to use that as an opportunity to learn, as an opportunity to remember the information that we learned during the course of the week. And with regards to the topic, I will give you tips on how to prepare thoroughly for your examination for this particular topic, as well as the marks that are allocated for this topic at the end of the year when you will be writing your technical sciences paper 2. So, without wasting any time, let us go to number 1 to look at what we are required to know as per the examination guidelines. Now, these are the definitions that are listed and they are defined, and we are required to know these particular definitions. Right, we'll use a purple pen for today. Now, the first definition that you have to know in this section is the definition of a wave. You must know how to define the term wave. And we say a wave is a disturbance. It's a disturbance. It's a vibration. And it is a disturbance that transfers energy through matter or space. Now, all of those keywords, they have to be there for you to get a mark, but they shouldn't just be there. They have to be in the correct context. It means they shouldn't be changing the scientific meaning of what a wave is altogether. So we know that, and we know this definition will be for 2 marks. Then we have the definition of reflection. And we say reflection is the change in direction of a wave. So it is the change in direction of a wave. And this happens, this change in direction of a wave, it happens when the light ray strikes the interface between 2 materials. So firstly, we know during reflection, the direction changes of that wave, of that light. When that light ray, or when the wave strikes an interface between 2 materials, so the direction definitely changes. Then we have the definition for refraction. Now, refraction, you see, we say it is the bending of light. Sorry about that. It is the bending of light. When it passes from one medium to another. So we definitely know that refraction takes place when light is definitely passing from one medium to another. And when it passes from one medium to another, the light bends. The light bends when it passes from one medium to another. So you need to remember that. And the difference again between reflection and refraction is that when we deal with reflection, we know the light ray reflects back to the original medium. But when we deal with refraction, we know that the light ray actually moves from one medium to another. Then we have what the critical angle is. Now, a critical angle, number one, learners will remember that it is an angle of incidence. It is an angle of incidence. And that angle of incidence, you will get it in the denser medium. You will get it in the denser medium. And this angle of incidence that is in the denser medium causes the refracted ray to just pass through the surface of separation of the two media. In other words, the refracted ray is going to act at an angle of 90 degrees. It will be refracted at an angle of 90 degrees. In other words, the angle of refraction is definitely 90 degrees. Are we together? Right. So, when you have a critical angle, my dear learners, it must tell you that it is the angle of incidence in the denser medium such that the refracted ray just passes through the surface of separation of the two media. So we note that it's still an angle because it's a critical angle, but it still represents an angle of incidence, but it will then have to be in the denser medium, and the refracted ray will pass through the surface of separation of the two media, meaning it bends far away from normal, such that the angle of refraction is actually 90 degrees. Then we must know again how to define the term dispersion. And we say dispersion is the phenomenon whereby light breaks up into its component colors. So it's a phenomenon, and the light breaks up into its component colors. This is where you remember that if we talk about white light, or if we talk about visible light, we know it breaks up into its component colors, and we have 7 of those colors. And those colors are red, orange, yellow, green, blue, indigo as well as violet, right? So it will be red, orange, yellow, green, blue, indigo, and violet out together. So they form what we call roid beef, but this is just an acronym, not even an acronym. It's just a nice way of remembering all the 7 colors that white light breaks up into, or what we call visible light. Again, from this information, my dear learners, there are facts that you are required to know. And those facts are, when you deal with violet, it will have a high frequency. So it will then mean it has a shorter wavelength because the frequency is high. So it has a higher frequency, a shorter wavelength. And because of this, we say it is refracted more. It will be refracted more. Then when we have red, we know it has a lower frequency. But if it has a low frequency, my dear learners, we then know that it will have a longer wavelength. Now, if it has a longer wavelength, then it will be refracted less. It will be refracted less. So just remember this very critical information. You must know that violet light is the light that is refracted more than any, and this is because it has a higher frequency and a shorter wavelength. And then red light is refracted less because it has a lower frequency but a longer wavelength. Good. Then we get to the fact that we are required to be able to discuss the following: the laws of reflection as well as the laws of refraction. Now, my dear learners, with the laws of reflection and the laws of refraction, remember what I said to you. I said there you need to know 2 of the laws for both refraction as well as for reflection. And I said, you can see it's not being discussed in the examination guidelines. So you need to understand the content for you to be able to discuss it. And I gave it to you and I said, you need to know 2 of each of the laws for both the laws of reflection and the laws of refraction. Now, let us remind ourselves about the laws of reflection. The first one tells us the angle of incidence is equal to the angle of reflection. Remember, we are talking about the laws of reflection. So we must talk about reflection. We can't talk about refraction. And I am emphasizing this, my dear learners, because you need to know the difference between reflection and refraction. Furthermore, my dear learners, you need to know that there is a difference between reflection and refraction. So the first law of reflection tells me the angle of incidence is equal to the angle of reflection. Secondly, the incident ray, the normal, and the reflected ray all lie on the same plane. So those are the two laws, and then you will get 2 marks. And then we have 2 laws again for refraction. And just like with reflection, it tells us about the relationship between the angle of incidence, but now the angle of refraction, because we are talking refraction. So the first one tells us there is a relationship between the angle of incidence and the angle of refraction when light passes through the boundary between the 2 media. Remember, at the boundary between the 2 media, for example, between air and glass, the light will pass through. And hence we say there is a relationship between the angle of incidence and the angle of refraction when light passes through the boundary between the 2 media. And the last one will say the incident ray, the normal, and the refracted ray all lie on the same plane altogether. And those are the 2 laws of refraction. Then we move on. We are required to discuss total internal reflection, and we are required to also define total internal reflection. Now, when we talk about total internal reflection, what are we talking about? Now, it says the definition, when the angle of incidence is greater than the critical angle, the ray of light reflects into the original medium. So that is the definition of total internal reflection. Now, when you analyze it, you will see that it basically gives us the condition of total internal reflection as well. But I want us to really remember that you cannot remember a definition if you do not understand it altogether. So it reads, when the angle of incidence is greater than the critical angle. This tells me, my learners, that there is no way that I will have total internal reflection if the angle of incidence is not greater than the critical angle. So the angle of incidence must be greater than the critical angle. And that is why the first part of the definition there, it says, when the angle of incidence is greater than the critical angle. Now, what happens then? We say the ray of light reflects into the original medium, and you will appreciate that it has to be reflect because we are talking about total internal reflection. And I'm emphasizing this because the wording sometimes becomes incorrect. When a learner is in a rush, they then write the ray of light refracts. So pay attention to detail when you give your definition. So the ray of light reflects into the original medium. And I want you to know that This word there, original, is critical altogether, because that gives the correct context of what we are talking about when you talk about total internal reflection. And I also wish to indicate to you, my dear learners, that when we deal with total internal reflection as a definition, we know there are not a lot of definitions that we have to know in this topic. And that is why we will most definitely ask you all these particular definitions. And that is why I spend time to make sure that you understand the definition so that you are able to remember it and you are able to state it altogether. Then you are required to be able to discuss the conditions of total internal reflection. Now, sometimes language becomes a problem. Now, what are we talking about when we talk about conditions? Remember, when we talk about conditions, we are talking about the requirements. So there we are required to discuss the conditions of total internal reflection. So you have to know the conditions, and you remember that it is two of those particular conditions, and I hope that you remember them. Now quickly look at the definition, because from the definition we actually have one of the conditions. Just giving you 15 seconds to really just look at it, and when I give the answer in your head, you also give it with me. And I'm telling you that the first condition is definitely in the definition. Right, I'm sure the learners are saying, Menier, by now we really understand this. And one condition that must be met for total internal reflection is the angle of incidence must be greater than the critical angle. That will be the first condition for 1 mark. The second condition will be that the light ray must be coming from an optically denser medium, or let me put it this way, it must be coming from a more optically dense medium to a less optically dense medium. In other words, the possibility of total internal reflection becomes available when the light ray is moving, for example, from water to air. Because from water to air means that it's from a more optically dense medium to a less optically dense medium. Secondly, you could say, for example, now I'm just giving you examples here. Another example is that the light ray could be coming from glass to air altogether. That is still from a more optically dense medium to a less optically dense medium. So those are the two conditions. Now I am saying this and I'm emphasizing it because we will ask you about total internal reflection. And I'm expecting that even when we give you a diagram, you must be able to check the path of the light ray from one medium to another, right? Meaning two media, maybe glass and air. And you must be able to check that will total internal reflection take place or not. Then you will just check that, oh, it is moving from a more optically dense to a less optically dense medium. the first condition is met. Then for the second condition, the learner then says, let me check, is the angle of incidence greater than the critical angle? And if you see that that is the case, you then say, most definitely, total internal reflection will take place because you would have met the two conditions for total internal reflection. I hope you understand that. Then we are required to state the uses of total internal reflecting prisms. And I gave you the two. And I said, at most, we will ask you for two. And we don't talk about a lot of them. There are quite a number of uses, but let us stick to something that we will always remember. And I said, firstly, it is used in optical fibers. That will be the first mark. The second use, it is used in endoscopes. And that will be the second mark altogether. So remember that, and that is all in terms of total internal reflection. And then we are required to talk about lenses, to understand lenses. Now you know, we look at two lenses, strict convex lenses and strict concave lens. So we deal with a convex lens as well as a concave lens. And we are required to be able to discuss the frequency and the wavelength of the various components of light. So we must know what is the relationship between frequency and wavelength. We need to know that. Secondly, we must be able to discuss and again be able to draw the transmission of light through convex and concave lenses. We must be able to do that altogether. So this is where now we are going to look at an object and the light rays coming from the object going through a convex lens or a concave lens up until an image is formed. And from that, we want to understand the properties of the image that would have been formed by the convex or the concave lens. So this is that, and we must be able to discuss how that light moves. For example, we know the light ray that moves through the optical center does not change direction altogether. The light ray that moves parallel to the principal axis is refracted. And when it is refracted, it then goes through the focal point. And that is when we talk about light rays that are parallel to the principal axis and so on. And when we then talk about a concave lens, we then know, my dear learners, that the light rays themselves are going to diverge. They will not meet at the focal point. And as a result of that, my dear learners, we know that this concave lens is diverging in nature, and we will still form an image and we will learn the properties of that image after we have drawn it. And you will see again, my dear learners, when we deal with concave lenses, that the image is always the same altogether. So remember that at all material times, we will remind each other of that. Which, for example, then, when you talk about a concave lens, we know the image will always be smaller than the object. The image is going to be upright, and the image is going to be virtual. And why are we saying the image is virtual? Because the light rays never meet altogether. Remember that. So the properties of that image is that it is smaller than the object, it is upright, and it is a virtual image. With convex lenses, we know the image is real because the light rays converge at the focal point. They are going to meet. Then we must be able to discuss the applications of convex and concave lenses. For example, convex lenses, we know they are used to correct an eye condition that we call short-sightedness. Short-sightedness. And we know when you talk about, sorry, just a point of correction. This one, it's far-sightedness. Here we go. It corrects an eye condition that we call far-sightedness. And we also call it, this far-sightedness, we can also call it hyperopia. That is a medical term for eye condition that we call far-sightedness, or we also call it hypermetropia. Hypermetropia. Right, so that is what a convex lens will do. Again, the application of convex lenses is that they are used to actually make magnifying glasses. So a convex lens is definitely used to manufacture a magnifying glass altogether. So those are other applications of a convex lens. Then we have a concave lens. And a concave lens is used to correct an eye condition that we call short-sightedness. Or what we call nearsightedness. Now, these are not different conditions. This is the same condition, which we then call nearsightedness. And the scientific term for that, it's actually what we refer to as myopia. Are we together? Right, we refer to that as myopia. So this is actually one eye condition. It is the same thing. Just like here, it is actually the same condition altogether. Then we must be able to give the properties of images formed by concave and convex lenses. So I've already alluded to that. Right. So my dear learners, we are done with the revision of this topic, and this is essentially what I take you through every day because I really want you to do well. Then here we are required to state the law of reflection of light. Now remember, the law of reflection, I told you, my dear learners, that it has two of those laws. The first one, now giving you answers there. The first one is that the angle of incidence is equal to the angle of reflection. The angle of incidence is equal to the angle of reflection. That is the first mark. There we go. And you note, my dear learners, very critical, we are still talking reflection. So a mistake that we often see is that a learner would write there, refraction. Number two, it says the incident ray normal and the reflected ray they all lie on the same plane. Right. So, my dear learners, check here. We are talking about the incident ray, the normal. We are not saying the normal ray, it is the normal. And the reflected ray, they all lie on the same plane. And this will be the second mark. Then they say in 7.2, how should a ray of light be incident on a rectangular glass block for it to emerge from the opposite side of the block without being refracted? Now, let us do this. Let us have the block here. There's a rectangular glass block, right? Let us draw the normal. This is the normal. Now, if I want this light ray not to be refracted, without being refracted, what must I do? The only way that I can make it not to be refracted is to actually shine the light in a direction that is perpendicular to the surface of the glass block. If I shine it straight like this, then it will not be refracted. It will emerge on the other side without being refracted altogether. In other words, how is it supposed to be? The ray of light must be perpendicular to the surface. It must be perpendicular to the glass block. So if it comes like this, you see, this is perpendicular because this light ray acts at an angle of 90 degrees to the glass block. As a result, my dear learners, remember this, remember, it has to be perpendicular. If you were to bring it at an angle, like this one, let's say you brought it at an angle, then it would be refracted. But if you bring it like in red, perpendicular to the glass block, it will not be refracted. So that would give us 1 mark. And you must be clear in your detail. The ray of light must be perpendicular to the glass block. Then the next question says, an incident light ray, OA, enters a rectangular glass block from A with an incidence angle of 55 degrees. The angle of refraction, which is called R, is 40 degrees. After refraction, the ray of light continues in the glass block and strikes the boundary at B, emerging into A. Then you are required to draw a fully labeled diagram, a fully labeled ray diagram, which should not be to scale, to show the path of the light ray through the rectangular glass block, indicate the magnitude of all angles. And this is for 6 marks. I know if you were to be given a question like this, you'd be so happy because you would get all the marks. Now, I've read this question once, and there is some information that I got, most definitely, but here there are things that I need to thoroughly check and underline because they make scientific meaning. So we have an incident light ray, so we are going to name it OA. And it goes into a rectangular glass block. So not just any glass block, it is rectangular. And it is from A. So if it enters a rectangular glass block and it is from A, it means the light ray is definitely moving from a less optically dense medium, which is A, to a more optically dense medium, which is the glass. And we've been told that the angle of incidence is 55 degrees. And the angle of refraction is 40 degrees. So we know what the angle of incidence is, given as I, and it's 55 degrees. The angle of refraction as R, given as 40 degrees. Now, a quick reminder. We know the angle of incidence is the angle between the normal as well as the incident ray. And the angle of refraction is the angle between the refracted ray as well as the normal. So when we go and do this diagram, we must already know where do we place the angle of incidence and where do we place the angle of refraction. And furthermore, we were told that this light ray continues in the glass block and it strikes the boundary at B. So this will be the second boundary. And it emerges into A. And we know when it emerges into A, we actually have what we refer to as the angle of emergence, and the light ray that emerges from the glass block into A, we know it is called the emergent ray. Now, we were then required to draw a fully labeled ray diagram. Now, I want to emphasize this. We've been told that it must be labeled to show the path of the light ray through the rectangular glass block altogether. And all the magnitudes of the angles must be shown. Right, let us do that. So, here, I have a rectangular glass block. Okay, that was skew. Okay. Right, there's my rectangular glass block. And normally, we will then show the normal. I'm going to label it for you. And then we will show the incident ray. Okay, needs to be straight. Good. There's the incident ray. And remember, it is a ray, so we have to show the direction. Remember, without the direction, you will not get a mark. And then this medium, they told us that it was moving from A. And we know that this ray is the incident ray. Now, the incident ray is the ray of light that strikes the glass block. And there I have made an arrow to show that a light ray has direction. And then from the normal to the incident ray, we know the angle is 55 degrees. In other words, it must have a degree sign. Then we are told that the ray is refracted Now a ray will only be refracted if it moves into the second medium altogether. Now when it moves into the second medium, we know it is made up of glass. So the light ray is moving from a less optically dense medium to a more optically dense medium. So the light ray will bend towards the normal. Then this light ray, we will call it the refracted right. So there's the refracted ray. And if this is the refracted ray, then the angle between the normal, which is this line, and that ray is the angle of refraction, which is given as 40 degrees. It's 40 degrees. And remember, this is towards the normal because the light ray was moving from a more optically dense medium to a less optically dense medium. Are we together? Right, just wanted it to look even more nicely for you. Right, and that angle we agreed, it's 40 altogether, and that is the angle of refraction. And the light ray, you take it all the way with direction. Where it ends, this is the second boundary. So you draw the normal. There is the normal. So the light ray now moves from the glass block to air, which is less optically dense. And because it is less optically dense, then we say, okay, it's going from a more optically dense medium to a less optically dense medium. So the light ray, when it exits into the next medium, it will bend away from the normal. So there's the normal and it will bend away from the normal. And this ray also has direction, so you need to show an arrow. And remember, the diagram must be fully labeled. So this, you know, we call it an emergent ray. It emerges on the other side of the second boundary. And we know the angle between the emergent ray and the normal. We call it the angle of emergence. And the value of the angle of emergence is the same as the value of the angle of incidence, because we know the angle of incidence is equal to the angle of emergence, and it must be between the normal as well as the emergent ray altogether. So this is the medium and that one is air. So this is what you need to know in terms of the path of a light ray through a rectangular glass block. So incident ray, then the angle between the normal and the incident ray is 55 degrees, which is the angle of incidence. The angle between the refracted ray and the normal is the angle of refraction, and we were told that it is 40 degrees. And then the angle between the emergent ray and the normal, we know that is the angle of emergence. Are we together? So this is essentially that. And all the rays must be labeled, the medium or the medium must be labeled, and the rays must be labeled, and you will not give you a mark if you don't give us direction. So for all of that, my dear learners, we have 6 marks. So already from this question, we can see that we have 9 marks that we can really get and do well. Right. Then we get to the next question. The next question says, the magnitude of the critical angle in the diagram below is 55 degrees. The magnitude of the critical angle in the diagram below is 55 degrees. Now, let us look at this diagram. In this diagram, what I can see is I have a light ray, and this light ray is moving from a more optically dense medium to a less optically dense medium. So this is the first thing that I see there. That, okay, the medium where I'm getting the incident ray, it's the more optically dense medium. And the light ray is traveling to a less optically dense medium. Then we say, okay, what can probably happen there? Or what has actually happened? I have seen that the incident ray is being refracted. And when it is being refracted, it lies on the surface of separation between the two media. And we know that tells us something, because now this angle is 90 degrees. Now, what does this tell me? It tells me that this angle of incidence, has caused the refracted ray to just lie on the surface of separation between the two media. Now, this angle of incidence is definitely angle number 2. It is the angle of incidence. And the question is, why is it the angle of incidence? Because it is the angle between the normal and the incident ray altogether. In other words, this one is the incident ray. This is the incident ray, the ray of light, and angle number 2 is the angle of incidence. Now, we know definitely, if I have an angle of incidence like angle number 2, which causes the refracted ray to lie on the surface of separation between the two media, then that angle of incidence represents the critical angle. We say, okay, this is an angle of incidence, which is then the critical angle, because it caused the refracted ray to just lie on the surface of separation between the two media. And because we've been told the magnitude of the critical angle there, we know that it is 55 degrees. Then 7.4.1, you are required to define the term critical angle. And we say the critical angle is the angle of incidence such that in the denser medium, such that the refracted ray just passes on the surface of separation between the two media. So we definitely see, my dear learners, all the answers are there. Critical angle, it's an angle of incidence. It is in the denser medium, meaning in the more optically dense medium, such that the refracted ray lies on the surface of separation between the two media. It is the angle of incidence in the denser medium, such that the refracted ray lies on the surface of separation between the two media. And for that, we will get 2 marks. Then they ask us, which angle represents the critical angle? Write down only 1 or 2. Now, we've already identified that it must be 2, because a critical angle is an angle of incidence, and the angle of incidence must be between the normal and the refracted ray. So the answer there is 2. It cannot be 1. 1 is not between the normal and the incident ray. Right. Now they say the incident angle is increased to 65 degrees. In other words, now the angle of incidence is greater than the critical angle. Remember, the critical angle was 55 degrees. So if I continue further and I increase the incident angle to 65 degrees, it means now I am making the angle of incidence to be greater than the critical angle. Now, what are the implications of that? It means I see that this is actually another requirement for total internal reflection. Because for total internal reflection, the angle of incidence must be greater than the critical angle. And then we ask ourselves, will total internal reflection take place? And we start to think that, okay, the first condition is met. The angle of incidence is now greater than the critical angle. Then what is happening with the second condition? You will remember that the second condition is that the light ray must be moving from a more optically dense medium to a less optically dense medium. And we go back to our diagram. Is that the case? Yes, the light ray is moving from a more optically dense medium to a less optically dense medium. So I'm now expecting that total internal reflection will take place. And why can I expect that? Because I see that the two conditions for total internal reflection have been met. Now, let us go to question 7.4.3. They say to us, what will be observed? So, what will we see? Write only, the ray will move out of the more optically dense medium, or the ray will be reflected back into the more optical dense medium. So the first option tells us, if I increase this angle to 65, meaning the angle of incidence is greater than the critical angle, and the light ray is moving from a more optically dense to a less optically dense medium, what is going to happen? And the first option is that it will move out of the more optically dense medium. In other words, it will go into the next medium. Or it will be reflected into the more optically dense medium. Or it will come back. Remember, reflection is the change in direction. Altogether, will it be reflected back into the more optically dense medium? And the answer is that the ray will be reflected back into the more optical dense medium. That will be your mark. How do you know that? Because you will now have total internal reflection. And when we have reflection, we know the ray of light returns back into the original medium. And that original medium, remember, it's the more optical dense medium. Altogether, nice one. 7.4.4, you are required to write the name of the phenomenon observed in question 7.4.3. So when it reflects back into the original medium, we know that is total internal reflection. And that will be a mark. Furthermore, my dear learners, it should be clear to you that we will ask you about total internal reflection, so know everything about it. And they say define the phenomenon in question 7.4.4. Now, can you see that if you were not able to get the answer to 7.4.4, then you would not be able to deal with 7.4.5, because then you wouldn't have known the correct phenomenon there. So you would define the incorrect phenomenon. Now, what does total internal reflection say? What is the definition? And I told you it will be there in your examination. It says, when the angle of incidence is greater than the critical angle, the ray of light reflects back into the original medium. And that is going to be 2 marks altogether. And we can go back and look at our examination guideline. You see, when the angle of incidence is greater than the critical angle, the ray of light reflects into the original medium, and that we are going to award you 2 marks. And that is the end of that particular question altogether. Right, we go to the next question. It says, name the phenomenon where white light is spread into its component colors. And another word that they could have used there is break. So there they are talking about spread, but you also know that they could talk about break. A phenomenon where light breaks into its component colors. We know that phenomenon is referred to as dispersion. Even when we define it from our examination guideline, we say dispersion, it's a phenomenon whereby white light or whereby light breaks into its component colors. There it is, the phenomenon whereby light breaks up into its component colors. So that is definitely a mark because we are just giving the term. Then what attribute of light causes it to spread out into the different colors? And we know it is the frequency and the wavelength of the light. So it is the frequency and the wavelength of the light. And because of the different frequencies, because of its frequency and the wavelength, then it is able to spread out into different colors. In other words, it is able to be broken, or it can break out into different colors. Then they ask us, what is the name given to the range, or rather to a range of colors observed when white light spreads out into its component colors? So those 7 colors, the range of the colors, what is it called? We know when we have a range, the term that we use scientifically is spectrum. So you will say when white light breaks into 7 colors, we refer to that as the visible spectrum. And my dear learners, I have seen a couple of mistakes where learners write electromagnetic spectrum. You can't talk about electromagnetic spectrum there, because now when you say electromagnetic spectrum, you are talking about the range of the different types of electromagnetic waves that we have. Are we together? So this one is incorrect. Electromagnetic means the spectrum of electromagnetic waves, the range of electromagnetic waves that we have, the different types of electromagnetic waves that we have. That is electromagnetic spectrum. But there we are talking about the different colors of white light that it can break up into. So it's a spectrum of that light. So we call that the visible spectrum. And that is the correct answer for 1 mark. Then they ask us, which photons between yellow and green light have higher energy? Write only yellow light or green light. And I quickly want us to go back here. You see there, the 7 colors are red, orange, yellow, green, blue, indigo, and violet. I will just write it here. Red, orange, yellow, green, blue. You will write it in full, my dear learners. This is not the acronym. It's just a nice way of remembering. Red, orange, yellow, green, blue, indigo, and violet. Now we know violet is actually just next to what? To ultraviolet. And we know that red is right next to infrared. Now, what do we know? If I go from ultraviolet and let's say to infrared, we know the frequency decreases. So this one will have a high frequency, a shorter wavelength, but because it has a higher frequency, it will also have higher energy. Then frequency definitely decreases. Because there we have a low frequency, a low energy, but then a longer wavelength. So from this to there, we have an increase in what? In the wavelength, because it's going from shorter wavelength to a longer wavelength. Now, if you look at violet, right? Violet light will have a higher frequency than all of these and a shorter wavelength than all of the 7 colors that white light breaks up into, but the highest energy. So the question there was asking us, which ones have a higher energy between yellow and green light? So we go back, we say, okay, there is green, there is yellow. So when I go from right to left, then the frequency is decreasing. In other words, green light has a higher frequency, and as you go to the left, because frequency decreases, it means yellow light will have a lower frequency. What does that teach me, my dear learners? It teaches me that green light has a higher energy, rather a higher frequency, and we know the higher the frequency, the higher the energy. And yellow light has a lower frequency, so it will have a lower amount of energy. And you know why I'm saying the light with the higher frequency will have the highest amount of energy? Because H is a constant, so frequency and energy are directly proportional. The higher the frequency, the higher the energy. So our answer there is definitely green light. And you give a mark. And you must explain the answer to the question. H is constant. The higher the frequency of light, the higher the energy. So H is constant. So the higher the frequency of light, the higher the energy. And we know, and this is normally how I would do it, my dear learners. And this is what you do if you want to excel and get all the marks. This is according to this equation where we say is equal to HF. Another learner could have said H is constant, so frequency is directly proportional to the energy. Are we together? Right. Then, okay, my mouse was moving quickly. Let us look at another question. A plane mirror is used to reflect a ray of light. Use the diagram below to answer the questions. So we have a mirror, it's plane, and it is used to reflect, and that was put in capital letters to reflect a ray of light. Now, my dear learners, we know that definitely a mirror will reflect light. The truth of the matter is that 90% of the light, or let me put it this way, some of the light will be absorbed and some of the light will be reflected. So now the interest is on the light ray that is being reflected. And we must use the diagram below to answer the questions. Now let us look at the diagram. There we have the object. Are we together? There we have the object. Now, if we have the object, what is happening there? It means this represents the incident ray. This represents the incident ray. And there, I'm just showing the arrow. Then, angle number 3 is the angle between the normal and the incident ray. So this is the angle of incidence. It is the angle of incidence altogether. Then we know that it is being reflected altogether. When it is being reflected, we know this one represents the reflected ray. And because we have reflection, if this was the original direction, then this is going to be the change in direction, which represents reflection. So 20 degrees represents what? The angle of reflection. How do I know that it represents the angle of reflection? Because it is the angle between the reflected ray as well as the normal. Good, and there we have a mirror. Let us go to the first question. What is meant by reflection? Now, my dear learners, you have to know this. We know reflection is the change in direction of a wave upon striking the interface between two materials. So you go back, we just check there. It is the change in direction of a wave. And then it explains when, upon striking the interface between two materials altogether. And with that, you will get 2 marks. Then you are required to state the law of reflection in words altogether. So the law of reflection states that the angle of incidence is equal to the angle of reflection. Because when the light ray falls upon a plane surface, it is so reflected that the angle of incidence is equal to the angle of reflection. And the second one is that the incident ray, normal, and the reflected ray all lie in the same plane. And you see I'm using reflected. Then they say, give suitable names for the following lines. You see, the vertical dotted line and between A and C. So the vertical line there, I can see that there I have a surface. The vertical line is perpendicular to the surface. And that line is definitely the normal. And then that one between A and C. Between A and C, we have correctly identified that it is the reflected ray. Altogether. So I hope this is really clear, my dear learners. To say now, I have an object there, right? So the light rays are from the object and they strike the mirror and an image is formed. So the light ray that strikes the mirror is the incident ray, and the one that is reflected and giving you that image is the reflected ray. So most of you tend to be used to working with how you see things like from left to right, but there it was clarified to us that B is the object and A is the image. Then they ask us, what is the name of angle 3? Angle 3, we have talked about it. It's between the incident ray and the normal. So it is the angle of incidence. It is the angle of incidence. And look at that. 2 marks. The examiner is very lenient with us, wants us to get level 7s. Then, what is the magnitude in degrees? And I like this because people just give a number at times. The magnitude in degrees of angle 3. Remember, here I have reflection because the light ray hit a plane surface like a mirror, and it was so reflected that the angle of incidence is equal to the angle of reflection. So if the angle of reflection is 20 degrees, then angle 3, which is the angle of incidence, must be equal to the angle of reflection. And that is definitely going to give me 20 degrees. Are we together? It's going to give me 20 degrees. Then we also want the magnitude of angle 1. Now, my dear learners, angle 1 is very easy. Remember, the normal there is perpendicular to the surface. So there's the normal, there's the surface. So this entire angle between the normal and the mirror, which is the surface, must be 90 degrees. So if this entire angle is 90 degrees and the angle of reflection is 20 degrees, it means to take it to 90, angle 1 must be 70 degrees. So our answer there. Am I correct if I've written that? No, an angle there is measured in degrees. So I have to show the degree sign. So without the degree sign, you can't get a mark because it's not an angle. And now we must give 4 properties of the image formed by a plane mirror. Now, let us remind each other. And I'm going to write them down here. I told you that when you look at the mirror, the object and the image that is formed by the mirror, they are the same size. Image So the object itself, like you, when you're looking at the mirror and you look at the image on the other side of the mirror, they are equal in size. So our answer there is that the image is the same size as the object. The image is the same size as the object. That is number 1. Number 2, when you look at the image, literally looking at it, the image is upright. It's not inverted. Rather, it is not upside down altogether. It does have a left and right inversion, but we definitely know that it is upright. Let us look at the third one. I'll just put it there. Remember, the light rays never meet. The light rays never meet. So the image is virtual. That will be the third mark. the fourth mark, and these are the ones that I want you to know because they are very easy to remember as well, is that the distance from the image to the mirror is equal to the distance from the object to the mirror altogether. So when you look at yourself as an object, for example, the distance from the object to the mirror, it's exactly equal to the distance from the image to the mirror. And that is going to give you 4 marks altogether. So remember these 4 properties of the image that is formed by a plane mirror. So now we go to the last question of the day. And it's really not that difficult. It says, a ray of white light strikes a triangular prism. And you know when white light strikes a triangular prism, I expect dispersion to take place. And it strikes it at an angle. Good. And the light breaks up into different colors. Those different colors of light, it's component. It is the component colors of the white light. And we know again that component of colors, or those colors that make up one white light, it's 7 of them altogether. And we know we refer to that as the visible spectrum. Then in question 8.1, they say, write down the name of the phenomenon described above. I mean, when white light breaks up into the different colors, we refer to that as dispersion. We definitely refer to that as dispersion. Good. Then, into how many colors does white light split or break? We definitely know, my dear learners, that it is 7. And they ask us, which color in white light is refracted the least? And I quickly want to go back there. Right. Look at violet. It has the highest frequency. And when you go through the visible spectrum to red, it has the lowest frequency. And we said the light with the highest frequency is the one that is going to be refracted more altogether. So out of all this, visible light will, violet light will be refracted more than all these 7 colors because it has the highest frequency and the shortest wavelength. The red will be refracted the least because it has the lowest frequency but the longest wavelength. So our answer there is that the color in white light, which is refracted the least, is definitely red. And that's a mark. If you had to give reasons, you would say it is because it has the lowest frequency, but the longest wavelength altogether. And this, my dear learners, sums up basically the type of questions that you should be expecting in your examination. Now, I want you to know this. As I give you tips and mark allocation, firstly, the questions that you are going to get, they will consist, firstly, questions on reflection. Your basic reflection, for example, using a mirror. And that will be followed by questions on basic refraction. And with basic refraction, then you will have questions that lead you to total internal reflection. And then you will have questions that talk to lenses. And in lenses, we will ask you to give properties of the lenses, the convex lens and the concave lens, and we'll ask you definitely to also be able to give the differences. And we will also ask you about properties of convex lens image and an image formed by a concave lens. So you must know the differences and be able to compare them, or give the properties individually, even if you are not giving the differences. Furthermore, we will want you to be able to draw any of the two lenses, a convex or a concave lens, and the transmission of light from the object through the lens until an image is formed, with correct labeling as well. And then we will ask you questions on dispersion, where white light breaks up into its component colors. So the amalgamation of all these is going to help you to do well in this particular topic. And this topic is plus minus 41 marks, and I know that you can do it. For the mere fact that you are joining me for this particular lesson is because you have an interest in passing. So I want to say this to you: prepare, 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 and you will know how to deal with this topic. And also, when you view the videos, view them from when the topic begins, and that will give you a hierarchy of growth in terms of understanding the topic better. Thank you so much for tuning in. The most famous saying by Albert Einstein tells us that once you stop learning, you start dying. And I want to keep this one for you most of the time because it really has a meaning. Every time you are going to continuously learn, and do not be afraid to learn. Do not be afraid of learning new information. So send me questions again to stemdigitalschool@africa10gigs.co.za so that I can help you with any content issues or questions that you do not understand. I will gladly do so. I will definitely see you on Monday between 6 o'clock and 7 o'clock for another great lesson on technical sciences. Thank you so much for tuning in and enjoy the rest of the afternoon. Goodbye.